It's wonderful to be speaking to you. My name is Bruce Momjian. I have another talk later today that relates to this one, so I'll be talking about that. And then Ibrar has a talk tomorrow that also relates to this, so we have some hookups there. I'm very relaxed because this is a relatively easy for me. The last group I spoke to before this conference was 90 Amish people, so this is like going to be real easy for me. The guys with like the horse and buggy and stuff. So if you're curious, ask me later. I also didn't know when I walked in the room I was going to be speaking, so that's like a double, So yeah, if you can do that, and it went really well, so you can do that. Like this is easy. So I guess the harder your talks, you get a muscle, and now you're feeling like really confident. So my name is Bruce Momjian. I work for EDB. I've been there for 16 years. I've been with Postgres community for 26 years. I'm one of the core team members. The slides you're going to see today are actually at this website right here. So if you want to download those slides, look at them. There are 58 presentations on this website, and probably 98 videos of me giving these presentations. So kind of a wealth of information there. There's 640 blog entries, all categorized by topic. So there's a lot there. This is kind of a topic that's near and dear to my heart because I find it interesting. Having gone through with Postgres so many years, we've been through different phases of Postgres development. So when I started in '96, the focus was prevent Postgres from crashing, right? Because it was a university project and it didn't really have the polish for a production use in '96. And then we went into a phase where we were implementing the SQL standard, and then another enterprise phase. And surprisingly, that enterprise phase ended about 5 years ago or 6 years ago, which kind of surprised me because I didn't realize it ended until 4 years ago. So it ended, but I had been in that phase for so long that it took me a while to understand what phase we were now in. And now we're in the innovation phase. And frankly, the innovation phase is one of the most interesting because, as you know, open source innovates much better than proprietary software. So this is kind of going into our strength zone here. And I think, Peter said Postgres is the most rapidly improving database and a rapidly growing database. That's true, not only of proprietary, but relational, but open source as well. So across the board, Postgres future is looking very bright. And one of the reasons for that, frankly, has been the explosive need for non-relational data in certain circumstances. I have a talk on my website talking about the data horizons, again, at that URL, which talks about the fact that in the old days, all your data came in from punch cards or dumb terminals or order entry type of applications. And now we have data coming from GPS, from social media, documents, Internet of Things, right? And we want data warehouse also to be working on. So now we have all these data needs that really didn't exist, years ago. And as we become more digitized, the ability to capture that data and make use of it is more and more important. So the idea of having non-relational storage in Postgres is super important. Now, at 1:30 today, I will be talking about the history of Postgres and why it has been able to change so smoothly to add non-relational workloads. Has to do with the history of Postgres, goes back to when it was originally developed starting in 1986 at Berkeley, and the idea of an object relational database. So that's what I'm going to be talking about at 1:30, okay? I don't know what room I'm in, maybe here, but just so you kind of know that the evolution of why Postgres is actually so good at this and is so good at data warehouse and is so good at sort of connectivity and integration is actually has a whole separate story that unfortunately I don't have time to go into. What I'm going to talk about today is sort of the evolution from relational to non-relational. Some of the concerns, some of the advantages, and then kind of walk you through how we got here and why non-relational is not like a bad word. You know, I don't know how many of you have academic histories, but you know, we used to have like the second normal form and third normal form, and you had to have like this pure relational. And you know, it sounds great on paper, but there's a lot of really good reasons that you'd want to store non-relational in a database. And that's what we're going to talk about today. Okay, so relational's been around for, what is it now, I guess 52 years. That's kind of crazy. We're still using that same underpinning. Relational has had, you know, it's had challenges over the years. There have been other groups that tried to kind of usurp it. But what's really interesting that instead of being crushed, relational has adjusted, whether it's XML databases or object databases, and they've brought the better ideas from these other systems into relational, and they've become a better relational. But again, incredibly flexible, but the relational is not always ideal. And that's where you go from academic, you know, black and white to practical. Yeah, non-relational actually has a lot of use. So the normal layout requirements for relational are the idea of a row and a column and a table. We actually use some of the academic terms in the Postgres documentation. The idea of constraints, and of course the concept of normalization. Here's a link right here. If you download the PDF, you can just click on that, and then it takes you to the website or the video or whatever link I put in there. And that normalization and the requirement for join, again, there's a lot of good reasons for it. There's a couple good reasons not to use it, and we're going to talk about those today. The first normal form requirement for relational systems is the idea of a column or an attribute, again, depending on what term you use, can only contain atomic indivisible values. That's not going to be true for non-relational. Repeated groupings of individual tables, separate table for each related data, and having a primary key. These are kind of requirements, and again, they're good rules to follow, but you also need to know when not to follow them. And I'm going to be highlighting when that really is a case. So why would you maybe not want to follow it? One is query performance. There are actually some non-relational storage in Postgres that we use in the Postgres system tables. So the Postgres system tables, by their nature, use some non-relational storage methods. Why? Performance, because doing a join inside of a server while you're running a query is not always a great idea. And I'll highlight particularly the use of arrays in Postgres for some of our system tables are actually a really good use for performance reasons of allowing a non-relational data type, specifically arrays inside of our system tables. Query complexity, obviously, if you don't have to do a join, it's a little more complicated, a little simpler. Storage inflexibility, another reason. Storage overhead and indexing limitations. We're going to talk about that as well. Postgres has some really creative methods for doing index lookups when you combine some data in a non-relational way. And it's hard to do if they're in separate columns, right? And I'm going to talk about that. Abrar's talk tomorrow. I think his talk is at 3:50. Let me just verify when his talk is, because I was out with him last night actually, and I know it's a good one. Let me see here. There it is. I think it's way at the back. All right, I'm going to have to find out. Where is it? Well, there's a lot of Postgres talks tomorrow. All right. I'm sorry. Yeah, I know his talk is tomorrow. It's about Postgres indexing. And I think you're going to see me talk about indexing, but again, if you want to go to his talk tomorrow afternoon, Ibrar, definitely do that. So what are we going to talk about? We're going to talk about these 8 specific non-relational types. Now, some of them might surprise you. Why would you want arrays in a database? There are actually some good value to that. JSON and JSONB are obviously sort of a flagship use for non-relational. We've obviously become incredibly popular because of that. Character strings number 8, you may not think of those as non-relational, but they kind of are. Because if you can think of a character string as a collection of letters, collection of words, collection of combinations of letters, right? So there's different ways of thinking of a character string that can make it sound non-relational, right? And you may not have thought about this before, but it's valid. And there's probably, I think I'm going to show you 4 different ways, or 3 or 4 different ways of sort of processing character strings in some really unique opportunities for Postgres, and I think you'll be impressed. So let's, any questions before we start? Great, okay. So let's talk about arrays. Now, arrays are the one thing that, as I said before, Postgres uses as part of its internal system. We have a couple cases where we have to store permissions for an object, like table permissions. And instead of doing a join from the table to another table that stores the permissions, we actually store the permission as a set of arrays inside. And it's basically an array of character strings inside of the row, the table row. And we do that because we're checking permissions all the time. We don't want to be joining to another table while we're running the query. And just embedding that in there makes a lot of sense. But there are some values even here for user applications. Here we have an employee, and we decide that we're going to have a certification array. The reason I know it's an array is basically just that we've got these brackets here. Now, you could put a number in these brackets, but the number really doesn't mean anything. It's basically just for documentation. But that indicates that I have not a text field, but an array of text. Now, I might have decided to make a separate certification table, but you know, I just want to list some certifications in there. I don't want to validate it. I don't want a lot of fanciness here. It's sort of maybe it's just a throwaway field I just want to put in there, okay? And there's nothing wrong with that if you know that's what you're doing, and we can change it later if we don't. But right now, we're just going to make an array, and here I'm inserting an employee called Bill, and I've got 3 certifications for Bill there, okay? And if I do a select, the output actually comes with curly braces on either side, indicating that that person has those 3 certifications, all right? And finally, I can do some really kind of cool query stuff. I can basically say, give me an employee whose certification contains this particular certification. This special operator you're going to see over and over again. We call it the containment operator. It's something that's in Postgres, I think, for 7 or 8 or 9 different data types. And you're going to see me using a containment operator pretty uniquely across this presentation to indicate containment. Also, if you'd love to run this, you want to run this presentation yourself, if you basically just download this SQL file, it is literally the queries in this talk. So the way I wrote this talk was to write the SQL, run the queries, capture them, pull them into the text editor, and then write the presentation from there. So again, if you want to just kind of run it, you can actually just run that, and it'll run just fine. You can index arrays using a number. In this case, it's highlighting that the arrays are 1-based. They're not 0-based. They're 1-based, so that's the first one. I can call a function called unnest, which will convert my array into rows. So if there was some need for the array to be sort of scalared out so you can then join it to something, you can use the unnest command for that. This would be an example of using the unnest command to kind of break that out. Okay. I can also take a normal output, and I can use a function called arrayag, which will convert my row-based output into an array. So array ag is the opposite of unnest, and it will effectively just flip it out into an array for me. Any questions? Okay. Second one, range types. This is a weird one. When I originally heard about it, I didn't understand why it was useful. I trusted the people who told me it was useful, so that was smart. Basically, I don't know how many of you know Jonathan Katz, but he's been at the AWS booth. He works for AWS, and he's the one who got me most excited about these types. It's probably 12 years ago, but he saw the value of these range types, and I didn't really understand it. But I came to understand why he was excited later on. So feel free to talk to him if you want more details. So here I'm actually creating a column with a type called TSTZ range, which is basically saying timestamp with time zone range value. All right, it's a little cryptic, but that's what we called it. And you will notice that when I do an insert now into that column, I actually specify a start and a stop date time field or timestamp field in the single column. Another thing you might notice is the use of brackets and parentheses. This is actually significant. The bracket is an inclusive indicator and the parenthesis is an exclusive indicator, meaning that we're including this time, but we're excluding that ending time. And that can be pretty important when you're running queries. Now, as you can imagine, here's our containment operator, again, running a query and saying, give me the rental car that contains this particular time, and you can see that it comes out just fine. If I give a different time, it actually does not work. Okay. Yeah.
So this says time zone. I'm assuming the time zone is just whatever the default time zone is, unless one specifies something different.
So the way that the timestamp fields in Postgres work is that we effectively store the data in UTC. So you would get as output whatever. So you're right. In this case, because I have not specified a time zone, it would automatically assume my current time zone for that time. It would convert it to UTC, and then it would run it against the query. You can see that my time zone is -4 because, in fact, the output shows the time zone by default. But if you admit it, then it would auto. But I could specify a different time zone if I wanted. Yeah, it's very flexible. But internally, it's going to store as UTC, which is probably the best way of going at it. Yeah. So let's get a little more sophisticated example here. Here we have a generate series where we're actually creating a 10-year, one-day rental. So we're going to take one-day rentals, and we're going to pretend it happened for 10 years. So that is 3,650 some entries we're going to put into this car rental table. And I can actually do, tell me the rental car that is contained in this time, and you can see it happens to be number 2,162, and that works fine. However, one thing that always gets people is when you actually look at how the internal code is working. Right, so I have a talk on my website about the Postgres Query Optimizer, but effectively, the fact that no index is being used on this query is a significant problem. The explain tells us that we're getting a sequential scan. So that would probably mean it would work fine for a toy application, but once you start to do anything significant, you're going to have problems because it's going to be just very, very slow. So what we can do with this type, and we're going to see this over and over again, is we can create an index. In this case, we're going to create a gist index. All right. And again, I'm not going to go into what a gist index is. Ahmad is actually speaking tomorrow at 3 o'clock. What room is he in? Let me see. Oh, he's in this room. Ah! Maybe by tomorrow, everyone will know where it is, maybe. Yeah, so he's speaking at 3 o'clock tomorrow. His talk is basically a deep dive into Postgres indexing. And what he's going to talk about is not only B-tree indexing, which is your traditional relational and hash, right? But he's going to talk about things like gist indexing, gin indexing, Brin indexing for data warehouse. So here we're creating a special type of index that Postgres supports called gist. And once we do that, we then do the same query, and you'll notice we're now doing an index scan. So one of the tricks for a relational system to effectively use non-relational data is not only the data types, but you have to have indexing that knows how to make use of those non-relational types. And you're going to see a whole bunch of different indexing used as we go. Trying to do all this with B-tree is just never going to happen. I mean, the classic case for this one, just to give you kind of an example, the classic case for here, if I didn't have relationals, I have this one. This one would be my start, and then I have another column, stop, and then I have two B-tree indexes, right? But if you do a query like this, like give me the one that's, how does it do it? Does it do the stop one? Does it do the start one? If it does the stop one, the start one, it's going to be, okay, here are all the rows that are greater than whatever, and here are all those that are less than, and it has to kind of figure out which ones are in both. That's really inefficient, as you can imagine, right? Because you got to process and then go back. So the beauty of the gist index is that it basically creates a much more contained method of doing these type of containment operators without sort of the linear behavior of a standard B-tree index. The B-tree is great for linear, but anytime you're trying to do anything beyond that, you need specialized indexing, and gist is a great example of that. Any questions? Okay. Another cool thing about these indexes, and this is something that's very hard to do, is that you can also create something called an exclusion constraint. And what exclusion constraint says is don't give me any overlaps. Now this is kind of hard to do because in a relational system, you'd have to check to see if there's an opening and then do the insert. But then somebody else could also be checking for the opening and then do the insert. So how do you prevent an overlap? You have to do it something at the server level because it just wouldn't work well. Because with these exclusion constraints, you can basically say, and this is an overlap operator, I don't want any overlaps in my field, and therefore I don't rent out a car to two people at the same time, right? So anyway, that's I think a kind of a cool example also of some of the specialized indexing in use there. Number 3 is geometry. Now I'm going to talk about geometry, but you can extrapolate this out to the very popular Postgres extension, PostGIS, which is our GIS engine. It's the same indexing, the same ideas. Here I'm basically just creating a point field. It has an X and a Y in it, and I'm going to randomly put 1,000 darts into this dartboard. I'm a terrible, maybe I'm terrible, right? I'm just randomly throwing darts here, and I can do a query, and I can say, give me 5 darts. But I can also do something with the containment operator. I can create a circle of radius 4, and I can say, give me all of the dots that are contained in that circle, right? This is the third use of the containment operator now. And it actually tells me there's 5 darts which are inside that circle, okay? You might think that's kind of cool, but okay, you're using a sequential scan, right? Boo, we know that's not going to work well. So rescue is gist. We create a gist index on our point, and then all of a sudden, when we run the query again, we get an index scan. Yay, right? But that might not be everything we want to do. We might want to find the 2 closest points, all right? And that's another problem that's really hard to do. Remember, I'm talking about a bunch of things that are hard to do, like exclusion constraints. This is another one that's really hard because you want the 2 closest points to the center, right? So how do you do that? Well, in a traditional system, you'd have to like make a box and then say, give me all the points in this box. And if I have more than 2, give me the 2 closest ones. But then if there's not enough, I got to make the box bigger and then run it again and then make the box bigger until I get my at least 2 points, and then I can order them, right? What's cool about Postgres is we've got this, it's called the spaceship operator, but for obvious reasons, for those of you from very old school computer games, but it's basically the distance operator, and it's saying, take the darts, order them by distance, and give me the 2. We call that the nearest neighbor search. That's something that most systems cannot do. And it's something that obviously would be super valuable if you're writing an app where you want to find the closest. Closest bar seems to be the example everyone uses. I'm not a huge bar fan, but anyway, that's the example. Everyone, give me the 2 closest bars to my point. And usually it's just the closest bar, but you get the idea. And what's also interesting is that we can use an index for that. So we didn't have to do the make the box bigger kind of problem. This nearest neighbor search developed by our Russian colleagues years ago basically walks through the index to find the nearest ones without sort of having to make a box and getting it kind of to expand and contract like that. So that's actually really impressive. A lot of these non-relational things have come from our Russian developers. We've had Russian developers back to when I started. Some of them were before me. So there seems to be a lot of interest in Russia for non-relational types, whether it's this, the JSON, the full text search, all came from the Russian developers. So before the war, I used to go to Russia pretty regularly, and maybe someday if things get straightened out, I'll be back again. But it's a very difficult time for us, obviously, and we're still trying to figure out how to help the people in Russia and, of course, the people in Ukraine without obviously supporting any of the actions of the Russian government. And how do you do that for people who've been with you for decades? And how do you not make them feel like they're abandoned? But also, how do you honor the Ukrainians and the terrible things that are happening? So I have a blog entry about it, which talks about actually open source and how this really relates to open source and what would be reasonable for the community to do and what would be unreasonable. So it's kind of an issue that we've had to deal with. But I have a blog entry if you're curious about where we can help and really where our hands are tied in terms of open source. So it's really kind of scary, but we're doing our best. Any questions about that? Okay. XML. XML used to be the big thing, not so much anymore, obviously, but we do support an XML data type. It's not super full-featured. We do have things like XPath queries you can run on them. You can index them as arrays. You can convert them to text. You can even do non-root queries if you're familiar with how that works in XML. You can use the unnest command. We saw that already. You can even do something like convert them to unnest and then run them through like a text pattern matching through the array. It's kind of interesting. So there's a lot of really unusual manipulations you can do with the XML data types. Any questions? Yes, sir.
Without this becoming a rabbit hole, what has been your observations on the reduced use of XML over time? Like, what do you see people not like about XML and where they go into?
Yeah, so the question is, what are people doing with XML versus non-XML and where things are, where the industry's going? Yeah. So, there was a time in, I want to say the early 2000s where XML databases were going to be the future. I mean, I know we kind of laugh at that now, but it's like, I remember when in the 90s when case tools were somehow going to eliminate programming, which sounds ridiculous, but that's what everyone was saying in the 90s. I'm dating myself, obviously. But that was kind of true of XML. There was a lot of hype on the XML database area, and that this was sort of a way of abstracting out, handling non-relational data, giving a standard format that people could use. I think where XML really kind of fell over was, believe it or not, editability. It just, everyone loved the idea of this interchange format, right? And they had, you had style sheets. Style sheet's not the right word, but you had like a template you could put over it to make sure it was well formed and all these other things. But it felt like it just kind of went a little too into the complex for people. And in a lot of ways, I think almost it was developers who just kind of revolted at it. The first revolt was probably the Perl format, the Perl YAML, right? You start to see that, and you still see it. I remember Kubernetes is YAML based, or some of the deployment like Ansible or whatever, or YAML. So you started to see that kind of, because that was human editable in a way that XML could have been, but they never really went there. They just kept getting more complex and more complex. And then when JSON came along, everyone's like, okay, XML fit the bill, YAML was editable, and now this JSON thing is so closely aligned to the way the data is typically generated at the browser that it was real, because obviously JSON is linked to JavaScript, right? So it's kind of the native format. And if I think, well, what would natively generate XML? Really nothing. There's a lot of things that will generate XML, but they're generating XML because they want to generate XML. They're not really generating XML in the way that JSON uses XML as part of the language. And when so many things sort of shifted to web-based data generation, having that generation kind of pass into, and the editability, it was sort of, I almost feel like developers were like, we've been looking for a way to kill XML for years, and now we found a way. I hate to say it, and there's a lot of sense that developers choose what they're going to use. And I feel like the business people loved XML, but the developers hated it. And that's as a developer, that's how I saw it. I've been on a lot of XML discussions in the community. There's a lot, and we were happy to add XML and so forth. There's a lot of groans, really a lot of groans. So be as it way, yeah. So we have two JSON types, and this is a little confusing. We have JSON and JSON-B. JSON is the standard store the JSON as a text field. And if you're just putting data in and out of Postgres without manipulating it, JSON is great because it'll basically validate your JSON, and you can do some operations on it. But in general, it's really designed for just storage and retrieval. And of course, we have a lot of support functions that can be used for it. Here's an example of some mock data that I generated that we loaded in to a field. We can pretty print the JSON, again, that thing of editability. I can index individual fields in the JSON using this kind of operator. I can look at the email key. I can concatenate them together. I can even do aggregates on them. No, this is not aggregate. Here's like a check of the one for the other. Here's the containment operator, right? But to use the containment operator, I have to actually cast it as JSON-B, and I'm going to show you that in a minute. You can create indexes on the JSON field, but they're not really ideal because you have to do it for each key. So here's just me indexing just the last name key, just the IP address key. So I'm sorry, it only does that one, doesn't do the other. And I can even do aggregates on it if I want to, right? But things really start to take off with JSON-B because here we're actually compressing it. We're storing it in an optimal format. It has some very sophisticated indexing capabilities. I will tell you that we delayed the Postgres release for 4 months because somebody in Russia found a month before the release that the data didn't compress very well. And it was August, and somebody said, I ran some tests, and this JSON doesn't look very compressed to me. We're like, we think it's compressed. And it went for like a week or two, and we ran it, and we're like, oh, we did something. We didn't store it the way we should have. So 3 months of, and my boss is saying, people really want this JSON-B thing. We got to get it out. I'm like, You don't understand. Once we solidify this format, we can't change it. Like, and nobody remembers that we delayed our release 7 years ago, right? All they know is this JSON B is really great. So a lot of times you got to make the hard decisions even if people don't like it. My boss didn't do anything. He just sort of said, you realize people are really waiting for this. I'm like, I know, but we got to do the right thing because we have a long future ahead of us. And we did the right thing. So values are native JavaScript text, Boolean, number, or subobject. We can index all of the keys together. It's compressed. It's sorted. It does not preserve key order or white space, and it eliminates duplicates. So those are some negatives there at the last. So here's an example of a JSON where you can see the white space is preserved, the duplicates are preserved. Here, if I convert that to JSON B, you can see the duplicates are removed, and the white space is actually removed. So the white space after name now is gone. And the white space after age also is gone. And the ordering is different. Okay? So again, that's, I think, a good example of the differences. But where it really gets cool is you can just take the JSON B, insert a bunch of data just like before, but now we have a new index type called gin, which is basically going to index all the keys and all the values together. And what that means is I can now say contains, give me the rows that contain last name of Banks. I use an index, first name of Jane, same index, IP address of this, same index. That's really, really cool. Yeah.
Another question. Is there any time when JSON is a better option than JSON B?
Yeah, if you're just loading and unloading, you're not manipulating it at all. Okay. Yeah. Yeah. Because you aren't going to get it back the same way you put it in. The ordering is going to be different. The dupes are going to be removed, right? So it's something you have to understand. You're going to have that behavior before you go in. Yeah. Because if you're just storing a config file, for example, and you want to just load the config file in and then dump it back out to the app, you shouldn't use JSON B. Okay. Yeah. Yes, sir.
Why would you then not use just text?
So because the JSON B is validated to be well formed, and because you can actually use JSON operators on functions on it if you have to. Yeah. Good. Another type we have, and this is a little like make your heads explode, is row types. So row types allow you to take a multi-field row and store it inside another row. So here we create a data type called driver's license, and we use that driver's license down here as a column. So I can actually insert into the truck driver table, and I can actually create a row inside of it. You see this used a lot, particularly if you're doing trigger functions, because you pass a row into a trigger, so that's a row type, right? Or if you're manipulating rows in your functions, you would use the row type a lot. If you query it, it just dumps it out as a row. You can actually query inside of the field using parens. Give me the state of that, and it actually works. Okay? Any questions? Don't go crazy with row types. They're cool, but because when the application gets the row type, it's just a text string. There's no, you know what I'm saying? It's kind of hard for applications, client applications, to manipulate them. Okay. Character strings, and this is the final one. As I said, there's a whole bunch of ways of looking at character strings. I'm going to come walk through them as we go here. So first, we're going to load some fortune data in. I think it's the FreeBSD fortune file, if any of you go back that far, where you could actually type fortune and it would give you a random text string. So I'm just loading it in. And normally, if you're doing a query and you're saying, give me a string that equals the word underdog, you have to have it case matched. So underdog doesn't match here, but uppercase does. What you can do is to cast lower on the field, so then you can actually match an upper or lower. But the problem here is the indexing problem, because when you effectively Oh, here's our range type guy right there. Our range type gentleman has entered the room. Jonathan, I was telling them if anybody wanted an exciting jolt about range types, you would be glad to do that for them. Good. Yeah, see, I told you he was going to inspire you. There you go. Thank you so much. So this is the problem. When you call a function on a column, you can't use the index. But in Postgres, you can actually create a functional index, or an expression index, we call it, and then you can use it. It's kind of cool, right? What if you want to do a prefix search like mop? Well, you can, again, the problem is that that's going to use a sequential scan, but we do have a special indexing operator called text pattern ops for non-ASCII columns, and that does allow you to do prefix searching for a string. Okay? Now, this is just the baby steps. We're going to go more complicated. So what if we combine them? What if we want a lower of a string? Well, again, that's back to our sequential scan. So now we have to do a lower of the column and then make it text pattern ops, and then that one will use the index, right? So we were using both of them at the same time here. However, that might not be enough for you, so we're going to allow you to do full text search, similar to Elastic or Sphinx, where you can do a full text search in Postgres. Supports 21 languages, including Armenian. Yay! In Postgres 14, I was shocked at that. But I'm Armenian, so that's why I'm excited. It does stemming, which means it removes like word endings and plurals. It knows about those for 21 languages. You can do and or not searches. You can do synonyms and stop words. So here's typically how you would do it. You can notice, for example, if I'm in English and I say I can hardly wait, the I and can are stop words and they don't get indexed. The hardly becomes hard, and that's a stemming use. And we could actually do something like this to compare it. And we can even do a search to say, does this match hardly wait? Yes, it does. Does softly wait match? No, it doesn't, right? Which kind of makes sense. But then we can create an index on that, and we can do something like give me all the strings that have the word panda, pandas, and I get one match that says panda, and beautifully you can see that it uses a very nice index for that, which is super cool. We can do things like an and search cat and sleep. I get a match there. I can even do something like this, cat and sleep or nap. Having a cat, I can appreciate these things. And you can see I get two hits now. I get the sleeping cat and then the cat napping. And notice napping is stemmed away, so nap matches napping. Kind of nice. What if I want to do a prefix search? I can do that as well. With full text search, I can say begins with the letter zip, and I've got a whole bunch of matches there. And fortunately, it uses our predefined index for that. So not only can I do word searches, I can even do prefixes of word searches. That's what the cool thing about GIN indexes are. Maybe that's not enough for you, and you decide you want to look for combinations of characters. So not words, but combinations of letters inside of words. So here I'm looking for the word letters V-E-R-I-T. I get 3 matches. But boo, 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 I get a sequential scan, right? Because that's not going to work really well. So we have something called PG trigram. This, I believe, was developed by the Japanese. And what it does is it basically creates a special GIN index called GIN trigram ops. And when you now look for the word verit, you get the results. But we now use our special trigram index to allow us to look for letters inside of words. So we can also, and even with that, we can even do prefix searches with the trigram in the same way we did prefix searches with full text search. Okay. So what have we? So here's the index. And you can even do things like similarity. Of course, we also support Levenstein and stuff, but here you can say, so much for the plan, give me the strings that are similar to that, and you can notice the similarity score and then the strings that actually match. In fact, what's kind of surprising is that plastic actually matches the plan part. You see that? I wonder if it kind of noticed the plan and plastic. Actually, the PLA, I guess, is a match. So it kind of probably thought that was a pretty close. I got to fix the A there. That's a mistake, but the A should be red, I think. And fortunately, it uses the index, but again, we have other options for that. So what did we actually do? I created all of these indexes just in this section, just for character strings, right? Remember, we did the lower, we did the text pattern ops for the prefix, then we combined them, then we did the full text search, and here's the trigram, okay? And stepping back one more step, these are all of the containment operators for all of the data types. So you can see point, you can see JSON-B, you can see array, you can see box, here's the range type, here's the full text search, right? So we've got kind of a lot of these sort of involved in things that we've seen. In fact, it looks like, I think any range, I should have read that. That's as well. We did any range as well, okay? So that's all I really wanted to cover today. This final warning picture, these non-relational types are great, but don't get carried away. You're going to end up like this animal, okay? You know, it's sort of like the non-relational gives you a tremendous amount of power, but use it sparingly because the non-relational can get out of control because it doesn't have as much structure as a relational system. And you can end up with data, like data management issues if you're not sort of careful. And I don't know how that happened, but we'll just do that and go back to it. Okay. So thank you very much. I am out of time. I am here to answer questions if you have them. Yes, sir.
When we started with the RDBMS, right, like 20 years before, we have RDBMS, we have NoSQL, proper distinction.
I'm sorry?
We had RDBMS and NoSQL. We had a proper distinction about the use cases. But over the period of time, right, like we introduced the JSON type, which was
Yeah.
what ODB was doing. Now we're introducing the search, which Solar and Lucene was doing. Like, where do you see that both are going to be, and a couple of other NoSQL databases are also introducing the as-it compliance. So it means I'm kind of seeing the line is kind of getting.
Right.
So where do you see that?
Yeah, so you were evolving in the same, the question was where do you see non-SQL databases versus SQL? And the issue is that things are evolving. You're getting, like XML databases. Originally everyone was like XML and there's non-XML. Now we do XML. So we're just in this transition period where relational is sucking out the good things of non-SQL. Surprisingly, Postgres is faster than most of these traditional JSON databases. So that's kind of cool. Like we're faster than Mongo, which seems crazy. So I think over time you're going to basically see, just like Postgres before is sucked in, relational sucked in other technology, we're going to see the same thing. Thanks very much. I'm out of time. If you'd like to ask questions, please come on up. I'll be here. Thank you. Appreciate it.